Okay, so this is part 3 of our derivation of the D6d character table. We got through gamma 1 and gamma 3. We knew gamma 1 was ones across the board always. Gamma 2 was derived using the z vector. Gamma 3 was derived using the x vector, and we found that x and y transform together as this function. And now we can actually do something quite simple, which is we can just multiply, because z isn't equal to the totally symmetric representation. You can do this trick when z isn't equal to ones across the board. You multiply x and y and times it by z and get a new function, which is going to be gamma 4, which is how x and z, xz and yz transform. And so all we do is then just multiply 1 times 2, negative 1 times root 3, 1 times 1, 0 times something, negative 1 times 1, negative root 3 times negative 1, and negative 2 times 1, and 0 times something and something. And so that is an extremely fast way of figuring out what another irreducible representation is. But that's the end of those tricks. This is a quadratic function, of course. We have other quadratic functions we can do. We can think about z squared. That's another d orbital function, right? xz, yz, z squared. Z squared, though, is going to be 1 or negative 1 component squared. And so that's going to give us just gamma 1. That doesn't help us. But what about x, y? Okay, x, y, and there's also x squared minus y squared. Those are our 5 d orbital functions taken all together. So we just carry on as we normally do, recalling what x and y individually transformed like. But we know for identity, x, y has to go to x, y. For the S12, remember that's a C12 followed by a sigma H. Sigma H didn't do anything for X or Y, so really this was like a C12, and recall that we used the rotation matrix, which was cosine 2 pi over 12. I'm just going to rewrite that as pi over 6 minus sine pi over 6 and sine pi over 6 and a cosine pi over 6. And so what this is saying is that x actually transforms into, so when we have xy, x is going to transform into cosine pi over 6x minus sine pi over 6y. Using matrix multiplication rules, cosine pi over 6 is root 3 over 2. So we're going to have root 3 over 2x, and sine pi over 6 is 1/2. So we're going to have minus 1/2 y. That's what x transforms into. What does y transform into? Sine pi over 6x plus cosine pi over 6y. So that's 1/2 x plus root 3 over 2y. And at this point, we can FOIL that out, right? Factor this, FOIL this out. So we're going to get root 3 through these x terms, root 3 over 4 x squared. And then we have a minus 1/4 xy term. And then we also have a, I'm just doing this in my head here really fast, so we have minus 1/4 xy term if we multiply these two terms, then root 3x over 2x times root 3 2 over y. That's going to be 3/4 xy. So that's a positive 3/4. This was a minus 1/4. So minus 1/4 and positive 3/4 gives us positive 1/2. So positive 1/2 xy. And then we have this y squared term, which is minus root 3 over 4 y squared. And we can factor this out and show, factor out a root 3 over 4. And what's pretty neat about this is now that you can see that with this operation, xy actually transforms as a linear combination of xy and x squared minus y squared. Well, x squared minus y squared is our other d orbital function. And so we can put these in parentheses together. We know now that going back to identity, that xy went to xy and xy minus y squared goes to x squared minus y squared for identity. We have a dimensionality of 2, in other words, and right, because we have an identity matrix that explains this transformation. One's across the diagonal. X and y cannot be expressed without also invoking x squared minus y squared. So we take the trace across this matrix, and that gets us 1 plus 1, which equals 2, which is why we have a 2 here. We're not done for the S12 class though, because now what this means is we have to figure out how x squared minus y squared transforms. All right, and so how does this work? Well, we have to take this component, this was how x transformed, right? We have to square it. So let's do that because we're x squared. So that's going to be 3/4 x squared. Then we also have this minus 1/2 y term that we can square. So that's going to be plus 1/4 y squared. And then we have the two cross terms. It's going to get us 2 negative root 3's over 4. That's a negative root 3 over 2xy. Then we minus by y squared. So this is y. So we have to square this term and then remember that we have a negative sign here. So again, we have 1/2 x. Squaring that term gets us a 1/4 x squared. And this is a negative of that. So minus 1/4 x squared. And then we have this term, which when we square that, we're going to get 3/4 y squared. And then we have the cross terms, root 3 over 4 twice. We have 2 of those. But again, here I messed up because we have to remember that this is actually a negative, right? Because the whole thing was minus here. And so same applies for this point right here, minus root 3 over 2xy. And so what that ends up doing is now we can combine some terms. So we have 3/4 x squared minus y squared. That's going to be 1/2 x squared. And then we also have 1/4 y squared minus 3/4 y squared. That's going to be negative 1/2 y squared. So we can factor out 1/2 and factor out x squared minus y squared, which is very nice. And then we have these xy terms. It ends up being minus root 3, right, with both 2 negative root 3 over 2 xy. And so really what this tells us is that xy and x squared minus y squared, we can write a 2 by 2 matrix. It's going to be xy goes to 1/2 xy plus root 3 over 4 x squared minus y squared. And on this x squared minus y squared, we have a 1/2, and we have a minus root 3. And so then when we take the trace of that matrix, sorry, I deleted it there, but we had a 1/2 and a 1/2 along the diagonal. So when we take the trace of this matrix, that gives us our character for the S12 operation, which is just equal to 1. Okay, so I'll come back and rewrite what we had up here and put in a 1 for S12. All right, so I got our 1 in there. Now we're doing the C6 operation. We know that x, y, and x squared minus y squared transform together. So we just go straight along here. And what we're going to end up seeing is that if we had kept what we had previously done on the previous slide that I erased, constant, we would have, if we kept it in generic terms. So what am I going to do instead here is, well, no, I think we could do it generically, but I think there's only a few more cases here. So let's just go through it. Anyway, we'll just keep cranking along here. So here we're asking how x, y transforms, right? And so we know that we use a rotation matrix again. Now it's not pi over 6, it's pi over 3, 2 pi over 6. So cosine pi over 3, we have negative sine pi over 3, and we have sine pi over 3, and cosine pi over 3. And so xy goes as cosine pi over 3x. Cosine pi over 3 is a negative 1/2. So negative 1/2 x minus sine pi over 3y, root 3 over 2y, times the y term, which is root 3 over 2x, minus 1/2 y. And so again, we have to FOIL this out. So we're going to get negative root 3 over 4 x squared. Our cross term, let's do our y term here, is going to be positive root 3 over 4 y squared. And then our cross term is going to be minus 3/4 xy. And then we have our other cross term, which is plus 1/4 xy. So our on-diagonal component here, I can just simplify this part to be, well, we can factor this out, I guess. So let me just write it out. Here we go. So we get root 3 over 4 negative root 3 over 4 x squared minus y squared. Again, we see it goes to a linear combination of x squared minus y squared. And then we have this 3/4 xy plus 1/4 xy, which equals minus 1 xy. Okay, so then we do the same thing for x squared minus y squared, just like we did before. We're squaring this term. This is the x component. It's giving us 1/4 x squared plus 3/4 y squared. And then we have the two cross terms to think about. That's going to be plus root 3 over 4, but there's two of them, so it's root 3 over 2 xy. And we have minus a y squared, so it's going to be this term squared, which is plus 3/4 x squared. And then we have this term, which is plus 1/4 y squared. And so we already can hopefully see where this is going, but with the cross terms, which we don't really care about because that's going to get us x, y's, but we can write it out. Those are going to get, let's see, this is supposed to be a plus. No, this is supposed to be a minus. So you have to be careful here. Why is this a minus? And let's make sure that this is supposed to be a plus. This is also supposed to be a minus, right? Because we forgot that the whole thing is minus x squared. So anyway, this becomes, the cross term then becomes root 3 over 4, negative root 3 over 4 xy. There's two of them, but then it becomes positive because we have a minus y, so it becomes positive root 3 over 2 xy. We really don't care about that too much, these xy terms, because we care about the on-diagonal elements. But this ends up becoming what? Negative 1/2 x squared minus y squared plus root 3 xy. And so really, when I keep saying we don't care about the off-diagonal elements, because here when we take the trace of the matrix, we're going to get that xy went into something times x squared minus y squared. That component doesn't contribute to character, but this minus 1/2 does. So you're going to get a minus 1/2 there. If we want to, for rigor, we could write the root 3 over 4. At this point, we're going to get a negative 1/2 here and a root 3 there, again, not contributing to the character. We end up getting that the character is negative 1/2 plus negative 1/2. So the character of C6 is negative 1. Okay. For x4 is going to be, for S4 is going to be a little bit simpler. We can go ahead and erase most of this. I'll keep the rotation matrix because we're going to need that later. But for S4, it's a 90-degree rotation, so we don't have to use trigonometry if we don't want to. I mean, we could use pi over 4s and pi over 2s and stuff, but I don't see why we would want to do that if we don't need to. We know that for an S4, it's equal to C4 followed by sigma h, but again, we talked about many times already in this set of videos, x and y don't change when we're talking about sigma h here. So x, 90-degree rotation, right? X vector, as we've derived before, spins into y, and a y vector spins into negative x. So we got x going to x, y going to negative, x going to y, excuse me, and y going to negative x. So therefore, what we really care about here, though, we're doing x, y, and x squared minus y squared. Xy is going to go to y times negative x, which is equal to negative xy. So the character there is looking like a negative 1, but of course, we have to have xy and x squared minus y squared transforming together. So x squared turns into y squared because x went to y, and the negative y squared is minus quantity negative x squared, which equals y squared minus x squared, which equals negative quantity x squared minus y squared. So and our 2 by 2 matrix that signifies mathematically this transformation is just negative 1, 0, 0, negative 1. And so when we do that, we take the trace of the matrix, we get negative 1 plus negative 1. And so the chi, the character of the S4 operation, is negative 1 plus negative 1, which is equal to negative 2. It's got us a negative 2 up there. C2. Is that our next one? Oh no, C3, sorry. C3 is our next one, right? C2 is one later on. C3, so similar type of thing here, but now we're not doing pi over 3, we're doing 2 pi over 3. So we need this, we're back to needing this rotation matrix. I'm going to erase most of this here. And so we're just looking at pure C3. And so we have to ask ourselves, how does xy transform? Okay, we're ready to go. So xy transforms as cosine 2 pi over 3. Cosine 2 pi over 3, 2 pi over 3 is 120 degrees. So that is saying x goes into negative 1/2 x minus root 3 over 2y. And y goes to root 3 over 2x plus minus, sorry, cosine of 2 pi over 3 is minus 1/2 y. Okay, so we crank through this and we have to factor this out, just like we've always had to do. And so this equals what? Root 3, negative root 3 over 4 x squared. And then we have a plus root 3 over 4 y squared. Then we have the cross terms. The cross terms are minus 3/4 xy plus 1/4 xy. So that equals root 3 over 4 x squared and negative root 3 over 4 x squared minus y squared. Did we do this right? We got a negative 3/4 xy. Oh, we didn't do this right. This cross term has to be a quarter. Anyway, so negative 3/4 plus 1/4. So that's going to be negative 1/2 xy. There we go. All right. You do this enough times and you can kind of tell when you've made a mistake ahead of time. Luckily, x squared is going to be, this is x, how x transforms. So how does that square? 1/4 x squared plus 3/4 y squared. And then the cross terms are positive root 3. It's going to be positive root 3 over 2xy. And then we have minus this term squared. So we have to remember that there's a minus sign there. Minus 3/4 x squared minus 1/4 y squared. And then it's going to be plus root 3 over 2xy. Ends up being root 3 xy. And then we can factor out a minus 1/2 x squared minus y squared. So we have 1/4 x squared minus 3/4 x squared. That's because it's a negative 1/2 x squared. And then we have 3/4 y squared minus a 1/4 y squared, which is, I guess, a positive 1. And so our 2x2 matrix that describes this transformation is simply going to be negative 1/2, negative root 3 over 4, taking that from these coefficients, and then taking from these coefficients, we have root 3 and negative 1/2. We take the trace of this matrix and we get negative 1/2 times negative plus negative 1/2. So this was all, by the way, for the C3 operation, right? Can't forget what we're doing. Equals negative 1/2 plus negative 1/2 equals negative 1. So we got negative 1 right there. Okay, S12 5 times. S12 5 times. Well, an S12 5 times is equal to a C12 5 times, followed by sigma H 5 times. The sigma H 5 times is the same as sigma H once, but it doesn't really matter because we know that a sigma H 5 times is just equal to sigma H once, and sigma H doesn't do anything, right? It doesn't for x and y vectors. And we're dealing with x and y vectors here. Quadratic functions involving x and y vectors, but x and y vectors at their core nonetheless. All right. So effectively what this becomes is just an S5, a C12 5 times operation. C5 5 times operation. Well, a C12 1 time is a C12 1 time operation we would need to use as our rotation here, 2 pi over 12, which equals pi over 6. We're doing that 5 times, so it's going to be 5 pi over 6 is what we need in our favorite little rotation matrix here. So we plug that in. All right, and then we say, how does x transform? Let's erase this here so we don't confuse ourselves. We are doing s12 5 times. Trying to figure out this character right here under the 2s12 5 class. X goes as cosine 5 pi over 6 times x cosine 5 pi over 6 is going to be equal to negative root 3 over 2. So negative root 3 over 2x, and then the sign of that's 1/2, but we have a negative sign here. And then y is going to be 1/2 x and a negative root 3 over 2y. And so if we go ahead and multiply these things out, as we've gotten accustomed to doing many times so far in this video, we get negative root 3 over 4 x squared, and we get the y terms here as being positive root 3 over 4y squared, and we get a minus 1/4 xy, minus 1/4 xy, and we get a, that's for these middle terms, and for the outer terms here, we get a positive 3/4 xy. And so what does that tell us that we end up getting? We end up getting this simplifying as 1/2 xy plus minus root 3 over 4 x squared minus y squared. All right, so that's 1/2 of this math that we have to do. The other half is figuring out how x squared minus y squared transforms. So we take this x component value, this x quantity, right, and square it. That gives us 3/4 x squared plus 1/4 y squared, and then the cross components are going to be plus root 3 over 2xy. And then we have the minus y squared, so we take this component as minus, remember to minus everything. So that's going to get us minus 1/4 x squared, and then minus 3/4 y squared, and then minus, but it's a minus of a minus, so it's going to be a plus of a root 3 over 2xy. That ends up equaling root 3 xy plus 1/2 quantity x squared minus y squared. We can factor out x squared minus y squared again, as you see this common theme. So we have 3/4 x squared and minus 1/4 x squared, and similar thing with the y squareds. So we end up with our 2x2 matrix looking like this, where we have 1/2 negative root 3 over 4, and we have root 3, and we have 1/2. And so then we take the trace of the matrix, we get that chi, the character of S12 5 times equals 1/2 plus 1/2 equals 1. All right. Next, we're doing a C2. The C2 is going to be a little bit simpler. So I think I should probably, for clarity, erase all of this. So this C2 that we're doing next is not a perpendicular C2, still coincident with the z-axis. Most of the classes in D6d, except for the last two ones, 6c2 prime and 6 sigma d, are coincident with the z-axis. So again, we got a 180-degree rotation we're doing here. We're doing a C2, And so we don't have to do any fancy trigonometry, fortunately. And so the math gets a lot easier, and we'll be able to calculate this relatively quickly. Why is that? That's because, right, on a C2, we know that x goes to minus x. We're doing a 180-degree rotation. And we know that y spins to minus y. And so this is C2, x goes to minus x, y goes to minus y. That means xy goes to minus xy minus xy plus positive xy. X squared minus x squared minus y squared is going to go to quantity negative x squared minus quantity negative minus y squared is equal to x squared minus y squared. Well, they all went to themselves. This is the identity matrix. So 2 by 2 matrix is 1, 1, 0. We take the identity matrix, we take the trace of the matrix, and we get 1 plus 1 equals 2 for the character. Easy peasy. All right, perpendicular C2s. Perpendicular C2s. Fortunately, how we define things is a perpendicular C2. So we define our perpendicular C2 to be on the one of them at least, which you only need one because all 6 are mathematically equivalent. We define one of them to be coincident with the x-axis. So we're thinking about rotations of the x vector and the y vector along the x-axis now. Well, of course, if you do a rotation along the axis that you're rotating like this 180 degrees, but your direction of your vector stays the same. So x goes to x. We did this way back when in the previous video when we're looking at this. But y is going to go to negative y. And so when that happens, then xy goes to x times negative y, which is equal to negative x. And x squared minus y squared goes to quantity, just goes to x squared, excuse me, minus quantity negative y squared, which equals x squared minus y squared. So that is equal to the that is equal to having a negative 1 here and a positive 1 here. And so now when you take the, right, just for completeness, writing this out, when you take the trace of the matrix, you get it equal to negative 1 plus 1, which is equal to 0. Sigma d's, last time we figured out that that was pretty hard to visualize when we're talking about x and y. Same thing's going to be true here, obviously even more complicated. So best thing is just to use your gamma 1 dot gamma 5 trick has to be equal to 0. Orthogonality has to be equal to 0. Gamma 1 we like to use because it's really easy because it's ones across the board, so it makes the math real simple. Basically goes away from the equation. And so as a result, we just have to normalize. We always just have to normalize for the number of operations in each class when we're talking about this orthogonality. So if we have an unknown value here, let's say we'll call it alpha, what this is going to be is 2 times 1 times 1 plus 1 times 1 times 2 plus negative 1 plus 1 plus 2. We're doing the dot product here. But again, we have ones across the board, so we don't have to worry about those. So I'm just going to write out 2 times 1, this first part, then 1 times 2, basically gamma 5 times the number of symmetry operations of each class. Negative 1 times negative 2, times positive 2, excuse me. Negative 2 times 2, negative 1 times 2, 1 times 2, sorry about that. Um, 2 times 1, under C2, and 0, so I'm not going to write it, plus 6 alpha, and all that, that's a dot product, must be equal to 0. I have a 2 times 1, that's a positive 2, I have a negative 2 there, those cancel, positive 2 and a negative 2, and I got two positive 2's, that's positive 4, and a negative 4 there. So 6 alpha has to equal to 0, so alpha is equal to 0. So I figured out this last one just using this little trick here, that is equal to 0. So a lot of work to figure out x squared minus y squared. Where do we go from here? We've done all the d orbital functions. And at this point, it's good to sort of check what we are expecting in terms of the dimensionality. We actually could have done this way in the beginning, but we have 24 operations here. 1 plus 2 plus 2 plus 2 plus 2 plus 2 plus 1 plus 6 equals 24. And there's this character table rule that I go over in character table videos, and we've used in a lot of derivation, that the sum of the squares of the dimensionality, so here I'll call it A, B, C, D, these unknown values, has to equal the order of the point group, which is order of the point group is the number of symmetry operations in the point group. So the sum of the squares of the dimensionality, that's the dimensionality means the character under E, the identity. So 1 plus 1 squared, 1 squared plus 1 squared plus 2 squared plus 2 squared plus 2 squared. I'm getting that from these values here, these 5 numbers here, plus a squared plus b squared plus c squared plus d squared has to equal 24. And so this is 4, 4, 4, that gets us 12, and then 14. So we're left with 10 left to parse over these 4 numbers. And so hopefully you can see that 2 squared plus 2 squared plus 1 squared plus 1 squared equals 10. And so that's just a nice little thing to do. You can do that at the beginning if you want, or whenever later on. But you know, we're basically looking for 2 more 2's, so 2 more sets of functions that transform together, and then 2 other ones that you know, functions that transform by themselves to get us where we need to be in terms of all gamma nines. This is a big character table, so you know, we shouldn't feel bad that this is taking us some time to do. But there's a trick. We can pull the same trick that we did in deriving x, z, y, z. We can now derive a cubic function, right? We derived this new one, x, y, and x squared minus y squared. We can multiply that by z. So that's going to give us a cubic function. And this is actually the symmetry of an f orbital. So you're probably not super familiar with f orbital, you know, functions. So this is a little esoteric. But that's going to be z times the quantity x squared minus y squared, right? These are f orbital functions. So I just took z and I times it by these parts. And so then I can do that and basically times gamma 2 by gamma 5, each of the components, to figure out gamma 6. So I got 1 times 2, of course, equals 2. That's what we expect because we have 2 functions transforming together. Then I got a negative 1 times a 1. That's a negative 1. I got a 1 times a negative 1. That's a negative 1. I've got a negative 1 times a negative 2. It's a 2. A 1 times a negative 1. That's a negative 1. And I got a negative 1 times a 1. That's a negative 1. 1 times 2. And 0 times something. And a 0 times something. And so, you know, this sort of has helped us before, gets us something very quickly, and it gets us another irreducible representation. Fortunately, at this point, you know, we can't really do that again, okay? Because it's without getting to crazy functions, and we're not necessarily going to get a function that's reducible, right? Like, or that's irreducible. Like if we do gamma 5 dotted with gamma 6, we're going to get a 4 here. That's a reducible representation because we know there's no 4's in this. Not a pure vector, not a pure irreducible representation. So we're going to have to turn to other functions in moving on from here. But let's take a break here, and we'll do that in the next video.